Hi all, I'm going to summarize the key points from the activity with equipotential lines, and in the process make sure we understand not only how to interpret it, but the relationship between them and the E-field line. So I'm going to keep this brief, come in with any questions. There will be a further tutorial that goes through the formalities of the equations that go with electric potential as a function of distance. You investigated that earlier. But the other tutorial will summarize those key points. All right, so an equipotential line, right? So you have two sets of lines that you can now put around a field or charges. You can put E-field lines, which indicate force. Equipotential lines indicate potential, which is related to energy. And what we want to understand about an equipotential line, and it's very similar, more similar to contour lines on a topographic map than E-field lines are, in that when you move along that, you do no work. Okay, in a sense, on a contour map, you're staying at the same elevation, so you're not working against gravity or with gravity. You're just kind of staying in the same place. There's still a force of gravity on you, okay, but since you're not exerting a force to move along that, you should be able to move along an equipotential line without any additional force. You do no work, okay, and it's still in the presence of a force field. Now, because there's two types of charges, how you interpret that work can get confusing. So I'm just going to do the case from low to high, and you can reverse it. So let's say I have equipotential lines where I'm starting at some negative value. It doesn't even have to be. I'm moving. This is my velocity in some direction where I'm going from low to high. There's two possibilities you have to understand. It could be a test charge that's positive that's moving that way, or it could be a negative test charge. We have a field here, right, that's creating these equipotential lines. So there's some field charges somewhere, but we're not interested in those so much as to how a test charge moves in that field. So the general rule is, and this helps to have this rule, is that if it's a positive test charge, you're going to do positive work. Okay, so if this test charge here, this blue one, is moving to the right as we go from low to high, we're working against the force, because one way to interpret this high potential right here, this equipotential, is at the peak of a hill. You're going uphill. So we're going uphill the whole way here, where zero is the flat ground. Negatives are like in a pit, right? They're below sea level, below ground. But either way, if I start low and I go high, I'm going up against the force, the net force acting on me. So I'm doing positive work. And why do we care that we're doing positive work? Because that goes towards a positive gain in potential energy, or a negative gain in, or loss in, kinetic energy. So I could have something that's initially stationary and I'm just moving it this way. I'm doing positive work because I'm working against a force, and at the end of it, it has positive kinetic. Excuse me, my bad. It has positive, it's gained potential energy. On the other hand, if I have, let's say, a proton that's initially moving with some velocity, and I just let it go, as it rises, or as it goes from low to high, it's going to lose that potential, or lose the kinetic, and gain potential. So the reverse is true if we have a negative test charge. You do negative work. So bringing having a negative move in this direction, it does it spontaneously. It wants to go towards the high potential because at the, if you will, somewhere in this region is a positive charge that's attracting it. And so what happens is then, in this case, the negative work means we're losing electric potential energy. Sorry, I just forgot how to write for a minute. And you're gaining kinetic energy. So I'll do this in blue. There's a loss in electric potential and a gain in kinetic. So that can be confusing. Now, the nice thing about this is, when I say from low to high potential, it doesn't matter what the field charge is. It could be two positives, it could be two negatives, it could be one negative, one positive. That rule still holds. And I find that's a convenient way to look at it. All right, let's turn to equipotential lines and field lines. So I've got two situations, and I asked you to explore those in the activity. So right here drawn is a positive field charge, and we see the field lines surrounding it. They're radiating outward. And what we want to understand is the way, if I were to ask you to draw equipotential lines here, and if you recall what you did in activity, there are circles, or concentric circles that surround it. And those circles are not equally spaced for equal increments of potential, right? So if I'm going to do equal increments of potential, I might start with something like this, and then I'd have to go, and then it's arbitrary. So let's say that this is a point source, so I've already got some distance from there to there. As I go to the next one, so let's say that represents 10 volts, so I'll put a 10 there just for example. Okay, if I want to draw a 20 volt equipotential, I don't go the same distance, I'd have to go a little further out. That's the nature of an inverse, and I don't know if I've made that necessarily a greater R, and if I want to go, that's 20, and so on. If I want to go 20, I go even further out. Excuse me, 30. Okay, and so we've got that, and hopefully what you noticed about the relationship between those lines is that the field lines are perpendicular to the equipotential lines at all places. And it actually has to be. If there was some component of the E field that was at an angle with equipotential, then that would make the idea of an equipotential moot, or would render it pointless, because the idea of electric potential line is I should have to do no work as I go around. Why do I do no work? Because the direction I'm moving is perpendicular to the force at that point. But if the force field is at some angle, then there's some component along my motion, and that would be a contradiction. So when you have a dipole where I have a positive and a negative here, the dark lines are the field lines. You should recognize those. We got the connecting loops from positive and negative. And then if you look at the equipotential lines, which are the fainter ones, you see they're drawn in such a way that at any point, if I look at this field line here, I'm going to trace this one again. If I look at where it crosses, it's always perpendicular. Okay? And if I want to put values on those equipotential lines, you should know this, that everything to this line, this bisector here, is important. That's at 0 volts. Okay? So at that point, you have no potential relative to the field, yet there's still a force there because we clearly see field lines there. In fact, the field is pretty strong right there, even though you're at 0 potential. So a common mistake is assume that at 0 potential, there's no force. That can't be. Okay, so everything to the left of this is going to be positive potential, and everything to the right is going to be at negative potential. So if we start here, you can think of it as being the peak of a mountain or a hill, and you're just going downhill, flat ground, and then into a pit. And this is based on the idea of a hypothetical positive charge, which would naturally go downhill away from the positive toward the negative. Okay? So patterns that we want to make sure we recognize and use on some of the following problems. E field lines are always perpendicular to equipotential lines. And so if you were given a map of equipotential lines, you should be able to draw field lines such that any field line as it crosses that potential line is going to be perpendicular. Okay? So you'll have some practice with that. This next one is actually a nice little thing. It's not immediately obvious, but it's implicit in all things we talk about. The direction of the electric field always points towards the lower potential. Okay? I cannot emphasize that enough because it's so easy to overlook that. If I go to this map right here, right, this is, the field lines are to the right. This is the highest potential, 50, 40, 30. Okay, maybe I got those numbers wrong, but 0, negative 10, negative 20. The point is, there is always the lines go from high to low. I'm not going to say from positive, negative. Even going this way from here to here, negative 10 to negative 20, negative 20 is literally less than negative 10. So we have to accept that. Take the negatives as an absolute term, not just a direction. And so if we go back to this problem, we can answer the same one. In fact, this is one of your practice problems, so I'll let you do that. Okay, lastly, the E field is strongest where the equipotential lines are closest together. And this is very much like a contour lines on a map. The contours show you equal elevation, and then where they're really closest apart, it's it's steepest. And if you go back to a previous tutorial where we related voltage to E, you remember that E is equal to V over D in that simple situation where a uniform field. So if we generalize this equation, we see that in a sense that E is the gradient or the slope of V. In other words, E is the rate, I shouldn't say rate, but it's the change in voltage as a function of position, not time. So if I go back to, let's say, if I look at this map here, the dipole, where I see they're closest together roughly in this region, the voltage change per unit distance is greatest, so that's where the field is strongest. So that's a useful thing to do. Okay, the problems that follow, some are going to be really tough conceptually. Give it your best shot. We will discuss them in class. I believe answers are given on the bottom.